So did you? Well, we have no rush if no one else comes. You've got the idea of periodic boundary conditions from the lab,
yeah.
more or less. So if you do have this hydrophilic and hydrophobic tails of barrier, you can, then it's opposite. You can select maybe, like here I'm drawing 4, but maybe it is more in such a way that they repeat to the left and to the right, the forward and bottom, and then encage it into VASP simulation cell with periodic boundary conditions. So if you describe, it will mimic infinitely long, and then one can explore how this cell membrane reacts to inorganic contaminant. You can put maybe cadmium selenium, or maybe the chemical agent that may induce euphoria. You know, this adrenaline, noradrenaline, and when you're happy.
Dopamine?
Yeah, like put it here and see how it just binds. Or just try different things, so it will be a very good model to check.
That's more my speed for for like a project. That would be very good for me to do.
Okay, so I'll look online, and you can look online also for atomic coordinates, EDB or XYZ of this phospholipid barrier. And I was already looking. What I found online, they do micelles when like 100 of these tails are making a globular structure. But you do not need globular with so many. We need just maybe four of those, and very narrow. So it will be long in the Z direction, but it will be really tiny in X and Y, so that we can do advanced electronic structure and do such things that typical. Well, there are a lot of researchers who do force field molecular mechanics for these barriers, but almost no. I never found that someone does electronic structure as we do here in class. And then if one selects small enough, one can get a lot. Oh, okay. Probably I have discouraged.
I don't think it has to do with you. I definitely think it's the spring break that comes
Oh, people are already ready to depart to spring break.
Maybe, but everybody has tests tomorrow. Because all of them, everybody.
So this class is unique, that we do not have tests.
Yes, yeah. So, it's a rough day tomorrow.
And how physics people manage to escape right in front of tests? Maybe their instructors also went to the same conference. It's like APS is a big thing for physicists. Well, I'll do my best to entertain, and maybe some points need to be repeated next time.
Hey.
Okay. There is no mute, there is no diary here on the diary. So maybe more people will come.
Maybe.
So what are we doing? We are going back to theory. So we need a background for density functional theory, which is I'm intrigued who is it. I don't know.
We have chocolate if you want.
Oh.
just
So
start.
we have a chapter on density functional theory, and it is not the best method in competition for high-level precision, but it is really reliable workhorse to describe properties of materials. And if we have models, we have a ladder of improving precision methods. We can always start with density functional theory to assess qualitative properties and then maybe go a little higher up for quantitative. So you see, it will keep us busy for about a month. And what will be today, and I may repeat it next time, there is a prehistorical density functional theory which is not used in any of our codes. It was, it is not called density function. It is Thomas Fermi theory that was designed same year as Schrödinger designed his equation, but it has all basic ideas in there. So you do not need, you can scroll back whatever, 90 years and get most of ideas of density functional theory just with basic quantum theory. And then we will go to modern stuff. If you like homeworks, it's a joke. Probably no one likes that. But it is an opportunity to exercise, and I will distribute it by email, so that the skill of making density of states will be supported by practice, because it is really needed for projects, and you may want to do it several times again and again. There is a last point, super extra credit. See here. So you may want to. It's extra credit. It is not mandated, but if you consider yourself as a potential researcher of perovskites, you may try doing it. So I will send by email a model of about 40 atoms. So 8 cesium, 8 leads, 24 bromines. And then your task, for those who decide to do it, will be to add periodicity along X, Y, and Z, and convert it into WASP and look for electronic structure and make density of states. If you have super large amount of steam, you can try adding a little bit different, like add 2 angstrom of vacuum, 1.8, 1.6, 1.4, or maybe 2.2, and see which amount of vacuum minimizes the total energy. You already know, Daniel knows from his experiment, that if you put 0 vacuum, it means this atom and this atom will smash into each other and energy will grow substantially. Will be like.
So does the vacuum just like put a space in between the repeating cells?
Yes, adding space, Vacuum meaning like you do not put any like hydrogens or water, you just put empty space, but a really small amount, like a couple angstroms. And you will find out that there is a magic number, like 1.7, that will minimize total energy drastically, and all others will make it expand. If you smash them into each other, it will grow very much. If you put a lot of vacuum, it also will be a little higher. So I'm trying to postpone hard time for me. Giving new material is always hard, and reviewing old material is always easy. Maybe on your side as well. So last time we looked on for the last time on Hartree-Fock that has Coulomb integrals in atomic basis, and the molecular orbitals are in form of so-called density metrics. And then you probably were trying to fill this flowchart with steps for the self-consistent cycle. During the lab last night, we saw how the self-consistency cycle goes on until the tolerance is satisfied, right? Then we recalled what are light waves, and agreed that if matter, molecule, nanostructure interacts with light, one has additional term in the Hamiltonian. And if one needs to describe quantitatively how much the light interacts with matter, which means in visible range, whether it is light is absorbed by molecule or emitted by molecule. It is characterized by matrix element of transition dipole. And we did a little exercise of trying to find transition dipole matrix element in multi-electron wave function basis. But after we did some math on the simple exercise, we found out that instead of many electron matrix element, it can be reduced to single electron matrix element. I needed to print it. But if you copy this slide in, it will be question number 2 or question number B in your homework. You can just write it down right now and then turn back. So, many electron system experiences an interaction with light. Elementary process is when light promotes one electron from occupied to unoccupied orbital, and all other orbitals stay non-changed. Therefore, they do not contribute to this quantity, which is called transition dipole matrix element. So, what is the elementary charge? Because we do with one electron. Then, in integration over only one electron degree of freedom, it is vector because the electron is three-dimensional. Then source orbital, where electron comes from, target orbital, where electron jumps to, for example, it can be HOMO and LUMO, and position operator, position vector. You do not like this equation? You don't do it? You don't?
Oh, no, I just have, no, I don't know why I was just making faces.
Okay, so it's irrelated to this.
Yes.
But we'll come back to this notation again and again when we will, at the last month of the class, when we will be describing optical properties. And maybe during the last practical steps, we will also return to it, because interaction with light is really important. One of the notations here, like excited and ground, or you can go from state 0, everything is ground, to excited state, which is characterized electron from orbital I jumped to orbital J. When you will, very much later, when you will do TDDFT, an excited state is superposition of several such pairs of orbitals. But right now, we are looking just on elementary stuff. Periodic. If you have repeating pattern, you can find positions in any repeating unit just by adding unit cell size vector, right? And if it is not only one dimension but several, you have several vectors for translation in X, Y, and Z, or maybe some non-orthogonal directions, but you can shift your unit cell in repeating directions. And the potential is periodic as well. So potential in neighboring unit cell is the same as in the source unit cell, where the wave function in vicinity of one unit cell and another one look the same way regarding to atomic part, regarding the part that gives you density. But in addition, there is a phase factor. Phase factor because the overall electronic wave function may move with constant momentum across several unit cells. And it is very, very, very normal in solids. We are just starting with software, but you have already seen that there is a specific file, k-points. So k-points is this k, the overall momentum of the electronic wave function. And last thing we did last time was theorem Koopman's theorem, right? If you drop Coulomb and exchange, the multi-electron energy of multi-electron state is just adding together orbital energies of all occupied orbitals. This is not correct. This is a very strong approximation, but it gives us a picture how to interpret it. And if you build a model that has different number of electrons, one less, which will be cation, or one more, which will be anion, and you subtract them, then under Koopman's approximation, it will be energy of homo or LUMO orbitals. But if you do research for publication, instead of using Koopman theorem, you better find total energy with different charge if you need energy of ionization, right? Those are subjects for presentations that will be in about 3 weeks from now. Well, 2 didactic weeks plus break week. Right? So 3 astronomical weeks. Last day of March, or last Thursday of March. And luckily there are 8 subjects and 8 attendees of the course, so it will be easy to decide what to do. So we kind of covered first 2 last time, and we will have 2 more labs before the presentation to cover the rest 6 things. So in some sense, we will come to the same or even better shape as we did with Gaussian. In addition to things that we were doing in Gaussian like orbitals, we will do absorption spectrum, and very important part that we will be doing molecular dynamics. Remember, Russell was showing the transition state search with some models, and Braden was showing happy turtle. So some people already know how to do this. But those were, how to say, one-way short models. But if you have sequence of reactions, or if you want to model materials at realistic temperatures, they are going on constantly, and motion doesn't repeat. It may do some different trajectories, but one needs to allow each ion to move freely, right? Especially if it is a liquid, or if it is a reaction when reactant bumps into a catalyst or something like this. So, what is density function theory in your opinion? You already know, Daniel knows because he was presenting. What is density?
Density. Density is the area where electrons are more likely to reside in.
Perfect. Yes. So until now, we were targeting multi-electron wave function as an intermediate object that allows to find total energy. In very narrow sense, computational chemistry is a tool to find total energy of any mode. I wouldn't agree with this, but some people believe so. And if you think so, then the users need only input geometry as input and total energy as output, and do not care what is inside. By now, we were targeting Schrödinger equation for multi-electron wave function as this inside object. And then we did split it onto orbitals that are fed into Schwader determinant and blah, blah, blah. Right? There are theorems, and we will come through them, so that instead of this truly multi-dimensional, 100-dimensional or higher dimensional multi-electron wave functions, one can formulate everything on a basis of 3-dimensional distribution of charge density. So no matter how many electrons, you just add together which space they occupy, as Daniel told me. Right? And there are equations that connect this very, very simple object. It is as heavy as one electron wave function. Right? So it depends only on 3 coordinates. And there are theorems that tell that one can find total energy and some other important observables based only on this distribution of charge. So having one distribution of charge instead of product of 100 orbitals is so much attractive. If it is possible, it really speeds up all calculations. So the main idea of density function is that instead of WF, wave function, you have charge density, CD, compact this. And you get total energy. Now you know what density function is. Right? So charge, density of charge, density of charge. Functional is how to get total energy. Well, there are some additional details, but in fact, it is main idea. And here it is so many coordinates, and here function of only one variable. Therefore, everyone loves it, even it doesn't give you super high precision, but the low price of any calculation is a deciding factor if you are shopping for mathematics. So we will cover everything that leads us to observables that allows to predict properties of molecules and solids. Observables coming out from practical algorithm, which will be very similar to flowchart for Hartree-Fock with little specifics. And then there are theorems, 2 main theorems. So we will be doing almost as mathematicians, proving that this crazy theory must work. And today I will try to cover background theory just for curiosity. I did it once in the past, and I was lazy to type it in, but I think it is, I cannot do better. So if you do have an orbital, you do your orbital conjugated or absolute value squared, and it is your theoretical interpretations of quantum theory, either probability density or charge density. Canonical interpretation of quantum mechanics is that it is probability density, but some people were thinking that it is charge density, and if you temporarily accept this point of opinion, it helps to get healthy derivations. Now, if you have only one orbital, you integrate it over all space, you get 1. If you do this only one electron, right? Again, I'm not telling actual density, nothing about actual density function of theory. Today, just entertaining you with preliminary steps. So a little piece of information here and there, so that later, when we will come through this big challenge of understanding theorems, you will feel much more comfortable. Those who do not have luck to attend today's meeting will experience harder times. Now, if you add together charge density for all occupied orbitals from first, second up to HOMO, right? Each of which depend on the same coordinate, on the same independent position. You will get things that Daniel presented last Thursday, and the last thing that we were looking at on last night lab, right? Charge distribution. Total charge of position. You know, if you integrate each of term, you get 1. Therefore, if you integrate summation of all these terms, you will get What? If you take total density and integrate it over the whole space, what would you get? Huh? You do not hesitate, it's simple.
Is it 1 still?
No. 1 if you integrate 1. 1 plus integrate second, you get 1 once again.
Oh.
Integrate, and then integrate orbital number homo. You get 1 plus 1 plus 1 plus 1. As many times as many electrons is in the system.
So n.
N, yes, number of electrons. If you have closed shell, 2 electrons up and down on each orbital, then it is 2 times homo, number of electrons. I'm going to tell you a secret. Now you know what is function. Not each functional, not density functional theory, but general mathematical concept of function. If you do have a function, so your charge distribution is a function, 3-dimensional function, and number of electrons is a number. So the procedure that converts a function into a number is called function. Okay? So the procedure that converts one number into another number is function. If you do like y as function of x, for 1x you have 1y. But if you have, instead of 1x, you have like 1000 x's function, but you still get 1y. This is called function. An example is here. You integrate your total charge density and you get number of electrons. Function. If you denote density distribution by letter rho and number of electrons as n, there is a very commonly used notation of using square brackets. So n square brackets of rho is function. And later on this notation, I may use it without giving you a warning, but now you have a heads up. So here is my plan for today, which I hope very much to complete. So even if I don't complete it, I just mumble and tell overall context. So we are not going to describe real world today. We're going to describe a fantastic universe, which has no ions, only electrons. And these electrons do not interact with each other. So it's like ideal gas of electrons. Crazy electrons just randomly move. This has no help for real life if you literally use it. But some philosophical, some mathematical concept that we may develop for this fantastic fictional universe may really help us to go forward in description of the realistic world. So it is a really good auxiliary tool. So why do we need this fantastic universe, fictional universe? And fictional means non-real, fantastic means super good. Fictional. Fictional universe, and what are we going to get from there? We do want functional. We do want an example of energy function. So since the main goal of computational chemistry is to get energy, total energy, we will try to check if we can do some manipulations in the fictional universe and derive equations for two things. One, total energy, if you know the number of electrons in this fictional universe. And second, density of electrons. There is no wonder if they do not interact, there is no ions and they move randomly, it will be some homogeneous distribution. So many electrons per cubic foot, right? But there is a way to make connection between total energy of the universe and density of electrons. If you will do it once for oversimplified stuff, later you will be able to do it for true universe with ions and with electronic interaction. Make sense? Fortunately or unfortunately, we are not first who are doing it. It was done, 90 years ago in 1928 by Thomas and Fermi. And then people have forgotten about it for about 40 years, and then started to coming back after the computers were sort of designed. So there are several steps that you can go through. And okay, I'll just try to go over. So the first idea is that we can split the universe on cubes, and it is our free-will decision how large the size of the cube is. Like the walls on the left and right, they also split on squares. Why can't we split our class on cubes? Imaginary cubes. We are not going to actually put any boxes. And then, if we know number of electrons in each cube and volume of each cube, then we have density, right? In some sense, we already know density. Now we need energy, which will be a little harder. Well, we can find energy of all electrons that sit inside one cube and then integrate over all cubes, add together, right? Energy is additive. So now we do have number of electrons, so this big delta, big N, inside one cube. So we know number of electrons in a cube with size L, and we know that they do not interact and there are no ions. Do you have enough background to find energies of electrons sitting in the cube of a given size? You were not taking quantum yet.
A couple years away.
Huh?
I'm a couple years away.
A couple years away forward, not backward.
Yes.
Okay. Then you will have this pleasure. Daniel? You got some quantum theory in your curriculum.
Yeah, lots of it.
Okay. So what is particle in the box?
The probability of where electron will exist, or distance.
Well, it is what's the main reason to study particle in the box concept?
I mean, there's like three well, if it's a single dimension, it's just you solve for distance.
You can solve for it.
Yeah.
You can solve. So it is enough. You told main word. So most of the real world problems are not solvable by pen and paper in literal mathematical radicals. Most problems are solved numerically, but there are very few problems that can be solved exactly. And particle in the box is one of them, luckily. So if you assume that there is a box and the particle doesn't leave the box, one can assume that there is no potential inside. It reflects from the walls and forms standing waves. And for the standing waves, you can find energy, right? Sounds reasonable. standing waves, electrons, and for each standing wave you can find energy. Like if you do have, standing wave, it means that it goes forward and backwards with some velocity very quickly, so quick that you do not discriminate whether it goes forward and backward. You think as superposition simultaneous, but you do have momentum or square of momentum associated with this motion. And if you, this equation shouldn't surprise you. High school physics, kinetic energy, mass, velocity, squared over 2. And if you tell in terms of momentum, it is p squared over 2. Right?
Yeah, I remember that.
Okay, then you're a right person. There is nothing new. The rest are derivations. So if you have this kinetic energy for one dimension x, and the momentum can be expressed as Planck constant quantum number divided by size. So there are several values of momentum which are allowed, right? And they depend on number of half waves, right? It doesn't surprise you. Half waves, standing waves. Yes, right? Since there are only discrete number of waves, there are discrete values of momentum that are allowed, and they do depend on integer number and x and size of the box. And if you want right dimension for momentum, you need the Planck constant. So as soon as you define size of the box, you know which, then you automatically introduce quantization. So the splitting of universe on the box was done intentionally, because the box is only one thing that we can solve. Energy contribution from motion in x direction, and if it moves in x, y, and z, there are energy contribution for each motion. So it comes in the second power because of momentum. Right? The higher the quantum number, the bigger the momentum, but momentum comes in second power. Therefore, quantum number comes also in square. Okay? And since motion along x, y, and z is independent, there are three quantum numbers for the box.
I just have a simple math question. If it's like the length over 2, and wouldn't that make it go up to the top? Maybe I'm misunderstanding what I'm saying. But like, instead of having
I can mess up with the factors. You are telling about this one gives 8.
Well, that would, yeah, that would give 4.
In the denominator. So you would tell that it should be like 4 here rather than the 8 there.
Yeah. Or like there would be 2 on top. Maybe I'm wrong.
No, it's fine. I can clean it up maybe for the next year.
Okay.
But right now we are targeting the main idea.
Yeah.
Yeah.
Okay.
Thanks for the good eye. So, which idea comes to your mind when you see 3 variables, each of them squared, and they are added together? Like if you were taking geometry,
Magnitude? Square it.
if you were taking geometry in high school, what comes to your mind? Huh?
The Pythagorean theorem.
Yes, Pythagorean theorem in 3 dimensions, if there are 3. Very good, very good. So if there are 3, like x, y, z, and you have so much in each direction, it will be vector, right? X squared plus y squared plus z squared will be length of the vector coming to this point, right? Length. And if you tell that x squared plus y squared plus z squared equals r squared, so equals constant. So each points that are offset from origin by the fixed radius. What is it? Which shape? Mathematically. Each point that is offset from origin by a fixed length.
A sphere.
Yes, perfect. Sphere. So we can think about sphere in this space of quantum numbers. We don't care what is the meaning of these variables. Instead of real space, it can be space of quantum numbers. And if you know that the radius is fixed, it means that energy is fixed. So in this space of quantum numbers, it will be surface of equal energy. And we need energy for the future because we need to find energy of all electrons. But we can play with this crazy space of states and identify in this crazy space a surface that you would correspond to equal energy. So if you go r squared and x squared and y squared and z squared equals constant, it will be sphere where all points on the sphere will have the same energy, will correspond to same energy of electron. So I will make drawing. I will draw spheres later, but if you look on the all states with energy where this radius between 0 and r, it will be energies of all electrons that have energy less than threshold. Everything inside sphere. Or we can look on the very narrow shell of a sphere, from r to delta r, right? You can imagine it and use it as our tools. For three lectures today and next following, we will think not as practical guys for real world calculation, but more like mathematicians. Theorems, abstract things, but it will be really, really helpful in reaching our practical goals. So going through these abstract concepts will help a lot. I was planning to reproduce this drawing, but you will forgive me if I show pre-made thing. I like making this picture again and again. I just calm down. So imagine me making these 25 points one by one. So if you forget about z quantum number and z quantum number and look only on two-dimensional thing, it's easier. You can quantum number and x, quantum number and y, and discrete quantum states. Why they are discrete? Because particle in the box is quantized. Only specific values of quantum numbers are allowed, right? Make sense? So we just equally fill the space with these quantum numbers. Each point means a state of a particle in three-dimensional box. And if we navigate, if you build a thin shell of a given radius plus minus something, it will be all states where this particle in the box has fixed value of energy equals n squared plus y squared, and if you have z plus z squared multiplied by some constant, where we had debate with Alice about factor 8. Now we were not wasting time when we visited geometry in high school. I hope so. So we can count how many states have this energy. We can count the area of this string. So for 3 dimensions, it will be this stuff. And if you do the volume, so if it is 3-dimensional and you count number of quantum states inside of this imaginary sphere, it will be volume of a sphere. There should be 5. Make sense? What's the volume of a sphere of radius r? Huh? Right? Oh, let me make a little test so that you are with me. What's the area of a circle? Not length. Area.
Oh,
So area is always second power. So length is first power, area is second power, volume is third power. So it should be r squared. Right? So how much? R squared. Everyone agrees. And volume is 4/3 pi r cubed. Right? So if we define the threshold, we can immediately, based on our high school geometry math, find how many states have energy less than a threshold. Okay. Good. If quantum number is always positive, then we have 8 times less, because if you split space on, what's the right name for this, quadrants or octants, if you like cut space on 2, for positive and negative 1 dimension, it is half. If you positive and negative for another, it will be quarter. If you cut it, slice it once again, it will be 1/8 of a space. And if you need the amount of this yellow states, it will be derivative of this 4/3 PR cube. Derivative and then the width of the string. So I'm not in a good physical shape. If I would be, I would stand on arms with legs upside down, two straight. You can even, you don't imagine it, but we are going to make mathematical inversion. So you can find energy right now. You did agree that you can find energy as function of this radius in this space of quantum numbers, right? But you can do opposite. You can find radius as function of energy. Make sense? So you can inverse. If the energy is something times r squared, then radius will be square root of energy. Make sense? So I will write it down, otherwise. So radius is square root of energy. 2 steps before, we did agree that number of states in this thin yellow stripe is radius to the 3rd power. But if the radius is square root of energy, we can just plug it in, this expression for R, into here. And then we get the amount of these states on the border is some constant times power 3/2 of the energy, of this threshold value energy. So it is just consequence of that our universe has 3 spatial dimensions. So if you have threshold energy and you have it in power 3/2, it will be amount of states with such energy. Okay? So if energy increases, the amount of states with such energy also increases, but as power 1/2. In some sense, this is density of states for electrons that do not feel any ions. So it's density of states of electron gas. You already know what density of states is in the sense of computational chemistry, right? It has like band gap and some. This is density of states for infinite, for the electron gas without ions. If you look like, if you have conduction band, then it grows only positive. So we have a couple of steps more. We need to recall what is Fermi-Dirac distribution. Give me a little science if you ever heard about it. Give me science if you never heard about it.
I've heard of it, I just don't got the knowledge to explain it.
It's here. All orbitals up to HOMO are occupied, all electrons starting from LUMO are unoccupied. This is Fermi-Dirac distribution at 0 temperature, right? And if you look at these models, at systems with band gap very close to 0 and temperature is substantially non-zero, then through the action of thermal environment, there will be promotion of occupation from HOMO to LUMO. Not complete, not 100%, but there will be distribution. So if this is number of electrons to HOMO, this is number of electrons to LUMO, at 0 temperature, it will be sharp step. So HOMO is occupied by 1, LUMO is occupied by 0, right? But if temperature raises, occupation of HOMO will be like 0.75, and occupation of LUMO will be 0.25. Make sense? So thermal activation, thermal excitation of orbitals, and it goes through this equation. But for our purposes, we need only this zero temperature example. So if you have the density of states as function of energy, we need only those that go up to Fermi energy, up to HOMO. So what happens to the rest of states, we do not care. We need only to take into account occupied orbit with given density of states. So this is protocol. How can we find total energy of system? So we add, we multiply. We need to find energy. We multiply it by the density of states, and we multiply it by probability that such state is occupied. So if we perform this integral, then we will get energy of all electrons in the box. So we'll take into account two factors. First, that the higher the energy, the higher the density of states. At higher energy, there are more states, on one hand. On another, if energy is above HOMO, states are unoccupied. So we need to integrate only from 0 to Fermi energy. And then we can drop this distribution. So we multiply energy by this density of states function, which is square root. And so that we do not argue with Alyssa, I put all constants as a constant, because I don't care what they are. So the only thing that we need to do is to multiply e power 1/2 times e, will be e to the power 3/2, and integrate. So it is a little exercise that we can do. So integral of independent variable in the power 3/2 dE. What should we get? Well, the answer is on there, but how do you get it? If you integral of x to the power n dx, what do you get?
Oh, sorry.
I don't care that they know. And I care that you know.
I do know it.
I,
It's x n plus 1.
uh-huh. So x to the power
N plus 1?
n plus 1. And the factor is either n plus 1 or n. What is the factor in front?
N.
Okay. And I put everything into the constant. So if your n, if n equals 3/2, then n plus 1 equals
5/2.
5/2. Yes. This here, right? And you explore it on the limits from 0 to energy Fermi. At 0 it is 0, at energy Fermi is 2. Energy Fermi in power of 5/2. So if your universe is split on boxes, you take one box, you know energy, Fermi energy from somewhere, then you know that total energy of all electrons inside this box will be Fermi energy to the power of 5/2 times some constants that Alyssa can help to carefully derive if needed.
I was just going to ask why it's 1/n instead of just n, but.
Because when you take derivative, the factor n comes up front.
Okay.
Okay?
Yep, I remember now. It's funny because I do this all the time. I just, when you like don't have actual numbers.
Okay. What did I wrote here? Number of electrons is a function of Fermi energy. Yes, we can do it. If we just integrate this density of states, you know the secret. If you make integral over all occupied, over density of states for all occupied states, you will get number of electrons. If you do your DOS in the lab, we were doing density of states from -10 to 0, right? Last night. But if you do it from as far to the negative as possible, from -100 or whatever is energy of lowest state, up to LUMO, so it will be like some complicated shape. And if you calculate the area under this curve, so integral of dose of epsilon from minus infinity to energy of HOMO, what do you get? Density of states is like number of electrons per energy interval. And if you integrate over all energy interval, you get total number of electrons. So we can practice the same. So this is our density of states, G of E. This is our Fermi distribution, which will be either 0 or 1. So we integrate density of states from 0 to Fermi energy, and we know it must be number of electrons. And if you take integral of independent variable into the power of 1/2, Alyssa can help us to take this integral. Same as before. Integral of e to the power n d e equals 1 over n, maybe n plus 1, no? E to the power n plus 1, right? If our n is equal 1/2, then result will be power 3/2. So it looks like kindergarten games, right? But we are getting something really, really valuable. So you got the number of electrons in the box is a function of Fermi energy. Fermi energy to the 3/2. So total energy is Fermi energy 5/2. Number of electrons, Fermi energy is 3/2. We are going to make a lot of benefit of it. So just summary what we got. Do we need Fermi energy ever? In our original discussion, we need to connect density and total energy. Fermi energy is auxiliary quantity that we can get rid of. So I have a suggestion what we can do. What if we express this total energy of a box with many electrons as function of number of electrons in the box? Can we do it? I know you can, each of you can do it. You're out of, no, you're not. Please try to do this exercise. It will be fun, it will be quick, it will take 30 seconds if you are tired and exhausted, and it will take 10 seconds if you are sharp at this point. Express delta E as function of delta n. Maybe next year I should be more intense on homeworks, not practical but theoretical. Do you have an idea? If you have an idea, direct yourself, do not wait for me. So, right now energy is function of Fermi, right? Can we take this red stuff and inverse it? So if delta n is energy Fermi in power 3/2, delta n is 3/2, which means square root in power 3. What if you take the root of third power of both sides? And then take a square of everything. 3 square equals. No, I need to go opposite side. No, I'm going right side.
Q.
Right? And if you do square of the third order root, it will be just delta n to the power of 2/3. Right? Did you get it?
Yeah.
Okay. And the next step is to plug this one into here. Right? So Fermi energy is number of electrons in 2/3. Delta n 2/3, and you plug it here, and then you get that delta E will be delta n to the power 2/3 into the power 5/2, right? So if you take 2/3 into power 5/2, what do you get? Huh? Yes, you cancel 2 here, and you get 5/3. If you would live 80 years ago, you would deserve a Nobel Prize in physics or chemistry or both, just for this little exercise. So you did this step, and you did this step. 5/3. So it is energy. You did a big discovery. You derived it yourself. Big discovery. You got energy of all electrons in a box as function of number of electrons. Only number, nothing else. This would be really good if you can do it for molecule. Number of electrons gives us total energy. We are almost done, and we are not too much over time. So if you have energy of, it's already written, I'm sure. We need to go from number of electrons to the density, right? So we can divide and multiply by volume. And volume is size of the box to the power 3, right? Box size cube. We will practice it in a second. Yes, it is here. So here is your discovery. Energy of single box is constant times number of electrons 5/3. Right? If you want to convert from number of electrons to density of electrons, you can divide it by L to the power 3 and multiply to the same power, L3 5/3. And since we are rushless and careless, we can call it a constant. Alyssa already volunteered to take care of constants if needed later, sometimes. So, number of electrons per unit volume is density of electrons. So, density of electrons to the power 5/3 is energy of one box, right? So, energy of one box. And R is position, is like where our box is located. If you go to the next box, it will be different R. So we need just integrate over space. So we take density of electrons to the power 5/3 and integrate over all space, right? Over all possible positions. 3 integrals. 1, 2, 3. X, Y, Z. Or R. And the constant, Alyssa, sorry, your nice volunteering suggestion to compute constant was already done by Enrico Fermi. It's all taken care and called Fermi constant. But if you would live 80 years ago, you could compete with him. So, total energy is summation of all boxes, or integration of all boxes if we make them smaller and smaller, infinitely small boxes, right? And it means 3-dimensional integral of density of electrons into power 5/3. This is incredibly important result. So if we assume that our universe, that there is a fantastic fictional universe with no ions and no electron-electron interaction, only kinetic energy, then the total energy of this universe is a function of a density. So you just need to integrate the density into the power 5/3 and you get the total energy. It is really, really nice. It would be really great if you can do it for molecules. And there is a hope that equation will be a little bit more complicated, maybe different power, maybe density plus something, maybe derivative of a density, but the main idea is that you see in this example, under some limits, you can convert density into total energy as a function. This is a main idea, and this makes all calculations so quick that you can just make electronic properties of very, well, I wouldn't say large, but moderate-sized systems. Really, everything else will be just adding on to this global idea. So integral of electron density, or maybe a little bit more complicated function. You have density, and you have procedure that converts it into total energy. What else? I'm almost done. It should be like seconds. Back. Back. So this integral, if I'm rigorous, I should put vectors. So this, in this expression, it is density under integral only local point, one point. It doesn't use density at point R and density at point R plus delta R, or nearest neighbors or over nearest neighbors. It is only one density in one point R, which means it is local. Right? Local. Therefore, all equations that have this functional form of integral of something in a local point is called local density approximation. And if you would, from your previous experience, if you go over Gaussian, choosing of methods, you choose density functional, and then in addition to basis set, you select functional. And you have, the first option is SLDA. You may recall. So the, write it once again. Here. Local density approximations, LDA. So what we did, to some sense, it is local density approximation, and with some little additions, it is already used in Gaussian. So LDA is the simplest possible form of density functional theory. And more advanced density, local density approximation, more advanced expressions include not only density at fixed point, but gradient, so derivative comparison of nearest neighbors. And then they are generalized gradient approximation, GGA. But main concept is already in LDA. The rest is just competition for precision. Well, I congratulate you with completion of this very important step towards becoming masters of density functional theory. I hope homework will not will complicate too much your break, and I expect that most of people will do it anyway after the break. So have a happy break, and if you are coming just for the class, see you in more than a week. If you are doing the research, we may see each other on Friday meeting at 4, Tuesday meeting at 4. If your schedule allows, you'll see announcements.